great.
Do you want me to introduce you quickly, or do you feel like you would rather introduce yourself uh, to everybody?
I can go ahead. Sure.
Yeah,
Thanks,
sounds
CJ.
good. Thank you.
I'm Mike Landry. I'm head of LIGO Hanford Observatory and a physicist with Caltech. You'll hear about LIGO today, and that's a very uh, large group of people around the world working on this field. And so hopefully we can go ahead and take this talk and have some questions. But it's a pretty small group, so I feel like if people want to just if they have a problem and they want to ask as we go, just interrupt me, and that might break things out more readily. So please feel free to just interrupt. Real small group. So thanks very much for the opportunity to talk to you all. It's great to be talking to a group of Canadian astronomers. I myself am Canadian. I was born in Montreal and lived in Calgary and Vancouver before coming down to the US as a postdoc in 2000. So I've been with this experiment for 25 years. Um, I'm calling this talk Gravitational Waves in Dark Sectors because one of my chief interests is sort of trying to understand aspects of the universe which are hidden. And gravitational waves was up until 2015, a sector of the universe that we had no ability to interact with, and now we have a way to detect gravitational waves in the laboratory, which is a hugely exciting development. Shown here is a artist conception Aurora Simonet from Sonoma State. It's a black hole neutron star merger, of which we have multiple different detections of these types of objects. I'm speaking on behalf of these large collaborations, LIGO Scientific Collaboration, that's about 1,600 people worldwide, half in the US, half around the rest of the world. Uh, Virgo Collaboration, which is French, Italian, Dutch, Polish collaboration, and also has teams around the world, about 800 people, and Kagra, Japanese collaboration with mostly collaborators in Japan and some in Asia. And LIGO scientific collaboration and the LIGO, particularly in the US, is funded entirely by the National Science Foundation. They funded the instruments, they fund much of the research that goes on in the US, and are enormously important component of the, funding that is right now under threat, and people are thinking how to ensure that much of scientific investment throughout the US is maintained right now. So it's an interesting topic. Okay, so let me go on. Here's a little outline. I'm going to talk a little about gravitational waves and sources. Hopefully, that's a little review if you've heard of them before. Um, and then talk about interferometers, the actual detectors we use to observe gravitational wave events. And then I'll talk a little about some astrophysics highlights and then talk about the current run that we're in. We stripe our data into observing runs. First run, first detections were made was just 4 months long. This particular run will be over 2.5 years when we're done this fall. And our prospects for the fifth observation run, we shut down for several years, upgrade the instruments, and you'll see why. The whole point is to reduce the noise in the detector in these breaks. And then we do a better job of finding gravitational waves in the future because our reach goes out by some component and the volume that we sample goes as the cube of that. That's really the wonderful thing about a gravitational wave detector. If you can get it, it's not often we have a factor of 2 improvement. If you can get a factor of 2 improvement in the sensitivity, your volume goes as the cube of that or a factor of 8. So your rate of events goes up by that. And then I'll close on new detectors. I might have to skip some slides. This talks a little long, and we've started a little later than normal. Okay, so GR and gravitational waves. So Einstein, worked for 10 years after special relativity, 1905 to 1915, to formulate his general theory of relativity. And in 1916, he made the first prediction. He actually got it wrong. There was a calculation error. Made a few of those in the following years in order to produce the what is the force carrier for gravity? These distortions in the metric of space-time, gravitational waves. which he characterizes here in the far field regime as sort of G mu nu is the space-time rhetoric, eta mu nu is flat Minkowski space, and H mu nu are these tiny perturbations, which we show in an embedding diagram as these little ripples in a flat, Cartesian space-time, a slice out of the center of these stars, plane of these stars. And H mu nu is the gravitational wave perturbation. And so what spilled out of his calculations is that they traveled at the speed of light, that they have two polarizations. They modulate, a circle of test masses, a ring of test masses in space, contracting on one axis and expanding on the other, and then vice versa, expanding and contracting. And that modulation, the frequency of which, if you're monitoring these, say, spacecraft in some force-free regime, either in free fall or in deep space with no forces acting on them, that the all of the information of the astrophysical source, whatever it's doing, whether it's black holes emerging or stars blowing up in supernova, that's encoded in the magnitude and the frequency development of this signature. But problem is the waves are really, really weak. So if you say take a, typical strain, a dimensionless strain, which would be the change in the length of, one of the axes that you're measuring. If you were made a ring detector, what's the change along one axis there? Delta L divided by the length of that, the diameter of that ring. That would be, a strain, and it would be dimensionless. And it's got these punishing terms. I hope you can see my cursor, 1 over r here. That's the distance to astrophysical sources, maybe megaparsecs to gigaparsecs. C to the fourth, I, G, all of these, yield strains of on the order of 10 to the minus 23, 10 to the minus 24. So it's a really hard experiment to do, and you need sensitive detectors to do it. Why would you do something like this? Well, you're trying to, tease out new sectors of the universe to interact with, to understand things that are new and different and you can't find any other way. So, a good example might be the early universe. If you want to learn about the early universe, you're looking at the cosmic microwave background that comes from something like 380,000 years after the Big Bang. That's important information, but it's also a lot of physics has happened between, the very earliest moments of the Big Bang and this 380,000 years at which light streams freely for the first time. Uh, if you find the gravitational wave analog of that, you'll be, looking at something like 10 to the minus 25th of a second after the inception of the Big Bang. So it allows you access to places that are dark. Problem is they're tough to find. So there are new unique probes, and there's lots of interesting probes, photons, and all the astronomy that you are all doing, neutrinos as details of what's going on inside, say, supernova, or from astrophysical sources like quasars, and subatomic particles. Gravitational waves are going to be produced by the most violent astrophysical events in the universe. They travel unimpeded through matter, which is what makes them a hard thing to detect, but two excellent probes of systems that are dark. They're expected to travel at the speed of light. You see, we have a measurement, first direct measurement of the speed of gravity on this, and they carry information about all this bulk motion of matter. So analogous to sound in some sense. So what are the sources that LIGO and these ground-based interferometers are expected to find? Well, in this quadrant plot, on the right column, we're looking at modeled waveforms. So these are things that we can use astrophysics and GR to come up with a waveform as to what we think it will look like, whatever it might be, say merging compact binaries like two black holes or two neutron stars or one of each, or the spinning of a pulsar if the pulsar has some sort of, deformation on the system. If it's, you can imagine a small mountain, a hemispherical mountain on one side or the other. And on this column, unmodeled sources for which we don't have good enough understanding of the systems to say we can use a matched template to analyze the data. So you have to do simpler things, eyes wide open things, burst-like sources, core collapse supernova, cosmic strings and cusps. And in this axis, the horizontal axis, top row is short duration events, and the second row is long duration events. So stochastic background, this one that primordial background I mentioned, long lived. Also something that we haven't expected to see. So if we find something completely uh, unknown, that will be very exciting. Happens all the time when you turn on a new type of detector, right? Jocelyn Bell and Anthony Hewish turned on a new radio detector that's sensitive to short-term variations and find pulsars pretty much immediately. Okay. Next, let me tell you a little about interferometers, the instruments that we use to detect gravitational waves. We said a ring detector in space is the sort of simple uh, thought experiment for how you detect modulations in space-time. If you consider that ring and just look at a Cartesian coordinate system with a vertice at the center of that ring, we're basically looking for the changing length of two arms. The gravitational wave strains aren't truly a changing length, but they give an observable in our L-shaped detector, which is the same. So here on the Earth, we have four large-scale detectors working right now. This is LIGO Livingston, our sister observatory in Louisiana. Here's where I am in the deserts of Eastern Washington, LIGO Hanford Observatory. In Cascina, Italy, a beautiful farmland, really good food. There's the Virgo interferometer. And in the same mine that houses Super Kamiokande neutrino detector in Toyama, Japan, is Kagra, the Kagra detector. Furthermore, there's a detector being built right now in India, LIGO India. This will provide the third leg in a three leg network of detectors, LIGO detectors. So 4 kilometer detector, just like ours, using NSF provided uh, parts. So we loan them $80 million worth of hardware, and they have provided the equivalent US dollars, 230 million in US dollars to build the site and hire the staff and install the interferometer and run it. So the whole point in this laser interferometer is, you know a Michelson interferometer from the Michelson-Morley experiment where you had light incident on a beam splitter. It was sent down and reflected and brought back and read out at an output photodiode. So similar thing here, except in the Michelson-Morley experiment, that was a four-legged delay line. So there was additional mirrors in that 1 meter space to make it four bounces. So it was effectively a 4 meter long interferometer, right? The longer the interferometer, the more sensitive you are to these differential displacements. In our case, we could make a delay line and have multiple optics in our 4 kilometer arms of the interferometer. But instead of having discrete paths, which make for really big optics, we have all those optical pathways folded down onto one. And becomes a Fabry-Perot cavity, a storage cavity. So if you consider this transmitted arm, what we call the X arm of an interferometer, can you see, Adrian, can you see my cursor okay here? Yeah, great.
Yes, yes, we can see it. No problem. Perfect.
Fantastic. Okay, so if we send light on an input test mass and down to an end test mass, this is a partially silver mirror. It's mostly reflective, but it might have a few percent of transmissivity. And so you can inject that light in and then servo the length of that cavity. You can't touch the mirrors, so you electromagnetically actuate on them. So you usually have, like upper stages, you may have magnets on one stage and voice coil actuators around the magnet. Same way a speaker works. You drive a particular AC current through that. You can create an electromagnetic magnet which pushes on the mirrors, pushes on the magnet which pushes on the mirrors. Or you may do that electrostatically as well on lithographed plates on optics. And the point is to servo this to keep this arm very still. Then all the light that would normally bounce off this, the 97% or 96% or whatever, that bounce off of this is coupled in and and resonates in the arm. So it becomes a storage cavity. On average, a photon bounces about 300 times in the arm. So instead of a 4 kilometer long arm, you have an effectively 1,200 kilometer long arm. Light leaks back through to the beam splitter. Same thing's happening in this arm. And finally, you overlap that, and you're on a near null fringe. You can think of this as a null experiment where the output of this interferometer is dark. And if the arm lengths change for any reason at all, then you leak light through onto photodiodes, and we register that. And so that tells us if the arm lengths change. It's not truly a null. If you're at a full null, you can't derive a error point to servo the arms. You don't know which direction to servo the arms when they start. So we usually set by picometers and then derive a sign for our actuations. Whoops. So you also see that this resonant cavity aspect of the interferometer is picked up and played all over the place. If we hold this on a null fringe, then all of that power is heading back to the laser. And so we couple that laser light in by dropping in, say, a power recycling mirror here. And now you can think of this mirror and as one input optic, like this one here, and everything downstream of this as a compound mirror. That's just light coming back from the interferometer. So you can think one mirror, everything else is another mirror, and we servo that cavity length and couple that. You get a factor of 40 improvement in the overall sensitivity of the detector in that way. Same thing with the signal, audio bands, sidebands, and this arm here. All of which makes for this incredibly exquisite detector, which has performance, sensitivity down to the level of, differential displacement of 1/10,000th the size of a proton can be detected. So it's incredibly tiny signal, strains of 10 to the minus 23, that sort of thing. Oh, one other thing, 3,000 kilometers separation means that you can distinguish signals approximately where they are in the sky through time of arrival. We'll see that too. Okay, so this is an important concept to get your head around. What's this plot? What's the strain plot of an interferometer? You have your differential arms wiggling away due to residual seismic noise that's leaking through that makes the arms wiggle a bit, or radiation pressure from the laser itself, and whatever makes this displacement noise in the interferometer. And you can take that light that's combining at the output photodiode. So there's always light there, as I said, for technical reasons, and there's junk light, higher order modes. There's some junk light there that you want to get rid of, you don't pay attention to. But nonetheless, if you take that light landing at the output of your photodiode, it's just some waving voltage as a function of time on your photodiodes. Take a second of it, make a Fourier spectrum of it, make an amplitude spectrum out of that, and calibrate it in terms of some known length. We push the mirrors around with auxiliary lasers with radiation pressure to exercise them through some known amplitude in order to establish just how much the arms are moving. And then you get what's called the strain curve, an output curve. If you divide that displacement noise by the length of the arms, 4 kilometers, you get these strains down 10 to the minus 23, 10 to the minus 22, 10 to the minus 24. So this is the target strain curve for some configuration in our interferometer. What we think the total noise will be is a function of frequency from 10 cycles per second, 10 hertz, to 100 hertz above a kilohertz. We sample the data at 16 kilohertz, and Nyquist is 7.8 kilohertz or something. So we can see up to, probably realistically, several thousand hertz. And at the low end, what are we limited by? Radiation pressure, quantum noise. This is radiation pressure at low frequencies. This is radiation pressure at high frequencies, the shot noise of the laser. So this would be a limiting noise source in an ideal interferometer. We'll see later that we're limited at low frequencies, in part by radiation pressure, but also by a lot of technical noise sources. We control all these different degrees of freedom in the interferometer, the lengths of all these cavities, the angles of all the optics, and some of that control noise and other things spill into the differential motion of the long arm. So and you can see things that you normally think of as being the limiting lines, say seismic noise, in principle, shouldn't hit us, but they do because of the roiling of the earth changes as a function of time. Sometimes there are storms off the coast of Alaska, or the Gulf of Mexico or the coast of Labrador and between Greenland and Labrador, and that microseism kicks up and allows us, it gives us difficulties in seeing. So Adrian asks, why does suspension thermal noise have strong noise in specific frequencies? It's a great question. So we'll see that later on when we suspend our mirrors, they're suspended by glass fibers, or upper masses are suspended by fibers themselves. And so they have their own, it's a room temperature experiment. So they have a kT of energy there. So they're vibrating away, like the fundamental mode of a suspended fiber or wire is a violin mode at 511 hertz. So if I look at this plot here, 2, 3, 4, 5, this is the sum of all glass fibers rocking the mirrors back and forth. You're just not sensitive there because the length noise at that particular frequency is governed, and its harmonics are governed by this fiber. Okay, so that's we talked a little about displacement noise, sensing noise, residual gas, quantum noise, and shot noise at high frequency. These are types of other types of noises. Some are true to displacement, like radiation pressure, uh, Brownian motion in the test masses. Uh, Good example. Yes, we said seismic. Yeah, thermal noises, those sorts of things. All right, so let's just a couple of slides to see the instrument. You don't have to worry too much about this plot, but the configuration turns out to be a lot more complex than I showed you with that simple schematic. But the primary things are here. You have a laser incident on a beam splitter, long 4 kilometer optical cavities, and about 95% of the laser itself is in the fundamental TEM00 circular mode with that cross section looking at the beam. You want that in the interferometer. You want to reject higher modes, which look like four-leaf clovers or pairs of blobs of light along different axes in many infinite higher order modes. So we reject those with a series of mode cleaners. And there's two input mode cleaners. Don't even show the smaller one here. There's an output mode cleaner which strips off junk light and higher order modes on the output. And there's a squeeze light quantum noise, quantum filter that we inject into the interferometer. So we'll see that in upcoming slides as well. So this is the primary laser, 1064 nanometer. So it's infrared light, and we use a series of amplifiers. We don't put in 200 watts. That's the design of the laser, but it's actually right now we only inject 60 to 70 watts into the interferometer, and it grows to nearly half a megawatt in the arms. So those optical cavities become difficult to control. That's why we don't just inject this straight up highest power we can right now. You have many optics sitting on seismic tables. So this table here is for smaller optics on the input and output stages, not the primary test masses. This is one in which the optical components sit on the tops of the tables. So it's got a single, suspended stage. That table itself is ultimately suspended from underneath by flexures. You have aluminum bars going to blade springs, which have flexures, which ultimately go back up and hold this table up. When you turn on the instrumentation on board, really high quality seismometers and feedback controls, that table becomes very still. And so the optics on top of it, which are triple suspensions typically, are also even more still because the platform itself isolates from the ground to a certain extent, and then the pendula isolate even more. The main mirrors, input mirrors and end mirrors, the 4 masses per interferometer, need better isolation. So they're suspended from above. So instead of setting something on a table, the primary test mass, which we'll see your actual version here, 40 kilogram silica test mass, is suspended by glass fibers to a penultimate optic, which is suspended by a series of multiple tables. And that quad forms a quad pendulum, 4 chains, making that test mass very still. That structure is suspended from a table, which is suspended from a table, which is suspended from another table, and that table itself has hydraulics to an external stage in the interferometer and outside the vacuum envelope, and you can move that entire payload to suppress things like the tides, the earth tides that stretch the crusts between the corner station and the end stations by plus or minus 100 microns over, uh, you know, 12 hours, or those storms off the coast that we talked about, all of which, achieves this very, very excellent sensitivity in displacement. Here's one of the main mirrors being reviewed. Actually, we're looking for perhaps points on the optic which have maybe developed. In what we found out what it was during the coating process, there's tiny flecks of metal that were getting burned by the laser, and that explodes a point to makes a impurity in the test mass coating, which makes the interferometric cavities difficult to control. This is the squeeze light source. So we can talk about this. This is the hardest thing to describe in the experiment. What is that radiation pressure in the interferometer at high frequencies, the shot noise, the statistics of photons arriving back at the beam splitter at low frequencies, radiation pressure. Those two elements compete to add noise. So you can inject an auxiliary laser, a so-called squeeze light source. You can squeeze it. You can think of the Heisenberg uncertainty principle, the variables associated with here, amplitude and phase of this light. If you squeeze in phase, and at the expense of amplitude, you reduce the overall quantum noise at high frequencies at the expense of low frequencies. If you squeeze in amplitude at the expense of phase, you reduce the radiation pressure, but increase the shot noise at high frequencies. So that's the squeeze light source. I've got a couple of slides on that. And then this is an older noise curve, but this is what the noise curve's looking like in reality. This is, again, that light arriving at photodiodes, put into an amplitude spectrum. So this is an amplitude and displacement with, numbers like 10 to the minus 20 meters here in the bucket. With good sensitivity, like that meets design for any given observation run, usually above 30 hertz. We've never made our noise targets at 20 hertz or 10 hertz. It's the hardest thing to do because of a variety of different sources. Okay. So let me go on. Oh, yeah, there's another question. Is there a reason why the laser is in infrared, not in the optical? Yeah, there is. And it's mostly a technical one. In the 80s, the 40-meter prototype at Caltech was green. It was a green laser interferometer. But a decision was made, and it was a very controversial decision in the small LIGO collaboration, then 25, 30 people or something. And it was to go to infrared lasers. It's primarily driven by cost and simplicity. Going to solid state lasers meant that you wouldn't have to, when you went to higher powers, like they were using milliwatts of power then to watts. When you go to hundreds of watts of power injected into the interferometer, as you knew you would at some point, that would become incredibly difficult to do with green lasers. And so the movement was made to infrared. But you can do the same experiment with green for sure, in principle. There's always these design trade-offs with a facility this big, right? How do you do this? Why 280 bounces? 300 bounces. Why not 1500? We could do that. But then the servos to control the interferometer, this very high finesse cavity, narrow resonance cavity, becomes very, very difficult to control. So if you make it too extravagantly difficult, you may have trouble just getting hold of your interferometer. All right, little on the network. We've already talked about these interferometers, but yeah, I just see the inception dates here, first running in sort of an observing mode. We ran LIGO Hanford, LIGO Livingston from 2001 to 2010 in something called initial LIGO, then shut it down, took out the guts of the instrument, left the vacuum envelope alone. Each of these are 10,000 cubic meters at 10 to the minus 9 torr. So really, really exquisite high vacuum, difficult to do. So we upgraded the optical components, everything, seismic isolation in the vertex and the end stations, and then started running in 2015. And our third day of stable running, we got our first detection. LIGO India, nominally 2030. We'll see when it really happens. Kagra is not online yet in a sensitive mode. And GEO is a smaller test, a 600-meter test facility with that the LSC is within the LSC. So it's high frequency, it has good sensitivity, so it's used as sort of a astro watch for supernova when we're down. And then we have sort of an extended detector. We ran with our second and third observation runs. We ran with, first and second observation runs. We ran with a private network of GCNs, which were sent out to astronomers in all types, radio to gamma rays, neutrinos included, in order to try to catch a counterpart should we see something that gives off electromagnetic waves. When two black holes collide, probably, if the black hole's charged, if there's a torus of material around it, it's conceivable you can get an electromagnetic signature. But the place where you really expect it is in the merger of two neutron stars. So I'll tell you about the observation of the first one of those, and we'll see that once we had done this once, we were able to go to full open network. Anybody who wants SAR triggers can get them now, follow up on them. So a little on the beam pattern, like detectors are maximally sensitive on the zenith. You can see the arms of our interferometer here and something that looks like a peanut. That's just telling you where's the optimal sensitivity. If this is sort of a unit one, vertically on the zenith, the z-axis vertically or down below the Earth doesn't matter. The gravitational waves passing over material basically unimpeded. So you're maximally sensitive on the zenith, plus or minus z. You're half as sensitive on one arm. If it's coming down one arm, you can imagine you got a modulation in the other arm, but not in an inline way on the arm that it's coming down. So it's half as sensitive. So that's half. And at 45s, you can see there's even a pinched null there, because if you have a gravitational wave in the plane coming at the vertex, then you have only common mode components. You have no differential sensitivity to something there. So it's a null in that. And so you just want these detectors all over at randomly scattered ways in order to maximize your sensitivity. Before I go on to the astrophysics, I just want to talk about the Canadian groups in the LSC. So if you want to contact them and check in with them. So Jess is at UBC, has a big active group there. Samar is at University of Manitoba, and Neil Dirksen is online and works with Samar and us at LIGO Hanford Observatory on detector type activity. Francois in Montreal is materials physicist. He is crucial in the thermal noise of coatings, working on coating thermal noise. And Sita, Maya's at Sita, where she does mostly astrophysics. So Jess does mainly detector physics and sends people to observatory here in at Louisiana. And Samar is a astrophysicist who works on compact objects, neutron stars, supernova, those sorts of things. So nice selection of instrumental work and data analysis. So if you're interested, please reach out to them. Okay, I'm going to touch on this. I probably have to really hurry on this section here. So I'll just note that the first detection you've probably heard of, two black holes, each about 30 times the mass of the sun, revolving around each other at 1.3 billion light years away. And at the time, this object was the uh, most powerful astronomical event ever witnessed by human beings, and none of it's coming out in light at all. It's all coming out in warped space-time. So really, really super exotic object. Fantastic day here at the observatory. We didn't know what we had all together fully, but it was clear it was very exotic, interesting, a potential object. By 3:30, three of us had vetted that this was not anything that we had injected into the interferometer, because we would run tests by making essentially fake signals by injecting into the detector. It took about 4 months to nail down, and then we published on February 11th, 2016. the first detection, and that's what this link is to here. 1708-17, in our second observation, I kind of alluded to this, that we had a private network in the first two observation runs in case we saw something with electromagnetic follow-up. And this was 100-second signal in our detectors, which when it's that long, you know that it's not black holes. It's got to be something very light. So when we got on the rapid response call for this at 5:30 in the morning, it was clear that neutron stars had been discovered, and there was a coincident gamma ray burst, which was so, weak because it was sort of off axis. No one would follow up on this GRB at all. Um, but we could tell that coming within, like 1.7 seconds of our merger was clearly the also co-located in the sky, was clearly the associated gamma ray burst with neutron star merger. This is the sky map that we produced about 4 hours later, I think. It took us a little while. Now we produce them within, 30 seconds to a minute. And including Z at 40 megaparsecs, 170 million light years. And so this event was detected first in optical 11 hours later by the SWOPE telescope. And SWOPE, I guess that's the collaboration, sorry, SWOPE collaboration. And what's shown here in this plot is, the time, which is linear here, and then logarithmic afterwards, of all the GCNs that came out this event. And so gravitational waves see this 100 seconds to the merger time, T0. And then 1.7 seconds later, so this is our gamma ray, or our gravitational wave detector, you have Fermi and integral showing a spike of gamma rays co-located in the sky at 1.7 seconds afterwards. So just like neutrinos followed the signature of the supernova in 1987A, here, sorry, right, neutrinos led the arrival time of light here in the supernova in 1987A. Gravitational waves lead. It's not that they're faster than the speed of light, we would think, but rather that it takes time to set up this jet, something on the order of a second, and for that to be to get out of this dense environment, right? So you can set a speed of, the difference in the speed of gravity limit by comparing these two, and I'll show you that in a sec. So then it was seen in all forms of electromagnetic radiation, from X to UV, optical, infrared, radio, everything. And tons of science was learned from this. Here's the different facilities around the world that looked into this. And this was the paper that was published on all of these different observations. So this was 3,600 authors, 200 instruments, 90 collaborations, and the hardest thing that I think I've ever been involved in to get everybody to agree on this paper. This is right now, the third most cited astrophysical journal letter ever, and it will surpass that, just given the rate of citations right now. But it was a real bear to land, but it was a lot of fun, incredibly fun time. So what was learned from these? First observation of a binary neutron star merger, first observation of a binary neutron star with gravitational waves and electromagnetic. I mean, it confirms this link with GRBs, the sum class of short GRBs and binary neutron star mergers. That was hypothesized way back in, well, probably early 2000s. There was many, many models. When I joined on in 2000, there was something like over 100 different models for what might produce short GRBs. And in 2005, Swift had shown there was a strong potential that neutron star mergers would be the source of these short GRBs, or at least some of them. And this directly confirmed that. This is solid evidence, not a lock by any stretch. We need more binary neutron stars, but it looks like heavy elements are produced mostly in neutron star mergers. So look at your watch, look at your gold, look at your silver, these things on your wrist, and you'll see that the material was made in binary neutron star mergers and then spat out into the galaxy about once per million years. First direct measurement of the speed of gravity, we measured the expansion of the universe in gravitational waves. These are really cool things. I'll just show you this. The speed of light is constrained. The difference between the speed of light and speed of gravity is constrained to be within a few parts of 10 to the minus 16 by looking at this timing differential. First direct measurement. In the first 3 observation runs, we made 90 detections. We're in the 4th observation run right now. I'm going to skip over these detections because I just want to close on the new stuff. So I can tell you more about these as we go. But these are the first 3 observation runs. This is our 4th observation run. You can see this big gap from 2020 to 2023. We got real slowed in COVID in building this filter cavity for the quantum squeezer for the O4 run. We'd lost about 9 months alone just in delays on steel for buildings for that. But we made improvements between O3 and O4, and each time you improve the sensitivity of the detector, you have this cubic effect in the reach on the volume of space and the rate of detections. So I'll come back to this in questions. I'm just going to show you this quantum squeezer. This is the squeeze light source here. It's a nonlinear crystal which takes green light, produces 2 red photons, and they're correlated and injected into the output of the interferometer, which interacts with the ground state of the electromagnetic field, which ultimately that ground state is a thing that interacts with the main laser and adds noise, produces quantum noise, shock noise at high frequency, radiation pressure at low frequency. So in this way, we were able to tailor that. And the filter cavity, the 300 meter filter cavity, this thing that we added during COVID, sorry, this piece here that we added in COVID, and in this little schematic, it's this thin tube beside the main 4 kilometer tube that goes down 300 meters beside the 4 kilometer main arm, and we resonate that. This is the actual filter cavity tube that allows us to. The addition of the filter cavity allows us to express better quantum noise at both high and low frequencies, which this plot shows. Okay, I'll just explain this plot for 1 sec. If you look at the black plot, that's our noise in our main interferometer without any squeeze light injected. Now, if we just inject frequency independent squeezing, meaning we squeeze in phase and add radiation pressure, then you get the green curve. These are actual curves at Hanford and Livingston, where if you look at compared to the black curve above 150 hertz here, we are doing better, a lot better in strain. The lower the strain, the better we can, further out we can see. And so we're doing better there, but at the expense, we're adding radiation pressure up here at low frequencies. And if we then do frequency dependent squeezing, meaning we inject the light into that filter cavity, which rotates the squeezing angle and allows you to do squeezing at all frequencies, then this is the curve that you get. And so you get this better low frequency performance here, purple curve, frequency dependent squeezing. So that lowers the radiation pressure. It doesn't like eliminate it, but it means that it's no longer the worst noise term that's spoiling your performance at 100 hertz or down at 20 hertz or 30 hertz. So that's just a huge achievement, really fascinating aspect to the experiment, and exploits this quantum entanglement phenomenon. I'm going to skip all this and just close by saying both Europe and North America have ideas for future detectors. In the US, that is something called Cosmic Explorer, which we really use similar technologies to something simple, but not so simple, which is to make the arms a factor of 10 longer. So instead of 44 kilometers, they're 40 kilometers long. And that allows you, if you look at the reach for Cosmic Explorer in pink, CE, that means that the reach for 150914. This is the location in Z of 5914, about zero point 0.1, that you will see with the both the Cosmic Explorer and the Einstein telescope, the European detector. You'll see all of the 3030 solar mass black holes in the observable universe. Yeah, the European version is very different. They don't have lots of land that's sort of available on 40-kilometer scales. And so they've gone to a much more aggressive scenario in order to accommodate the interferometer. So underground, 6 interferometers in a triangular configuration, where at each vertice you have a low and a high frequency interferometer. One's cryogenic, and one has high power. It's just difficult to do high power for excellent high frequency shot noise performance, and cryogenics, where you cool your test masses for excellent low frequency noise performance. So they stitch together two independent noise curves of the two interferometers at each vertice. So 6 interferometers, 3 vertices, 10-kilometer arm lengths. Might be in Holland, it might be in Germany, it might be in Sardinia. It's a difficult thing to understand what it will be. So I am going to close there and just say that there's lots of these different detectors that people envision. There's ground-based interferometers. We're kind of the gamma ray version of astronomy, high frequencies. You can do space-based interferometers down into the millihertz and submillihertz regime, so arm lengths of 2.5 million kilometers. In pulsar timing, in the nanohertz regime, they have this arrays of pulsar astronomers have really good evidence, or 4 sigma greater evidence for a stochastic background. It's probably the sum of supermassive black holes whirring around each other in the near universe. And then probably heard of BICEP 2 going on to BICEP 3. There's polarization measurements of the cosmic microwave background that may give early important information on the gravitational wave cosmic background. Yeah, I'll stop there and take some questions.
Thank you so much, Michael. It was super interesting. I really, really like the plots you're showing about the sensitivity of LIGO. Every one of them, I find them like so incredible that we are able to have such precision on like the the gravitational ripples of the universe. Like I find it incredible. Like it's fantastic. It's really fantastic.
It's why that took so long, right? I think so.
Mm.
Essentially, theorists in the Chapel Hill Conference in 1956 had done the thought experiments that allowed them to think, well, yeah, I think we can make a gravitational wave experiment to detect gravitational waves. And then Joe Weber made these resonant bar detectors in the 60s, and they were quite extraordinarily sensitive. They're resonant detectors, so they're only sensitive in a narrow band. They're not a broadband instrument like ours. And he actually thought he had seen gravitational waves, and that was a big controversy. Bars grew up all over the world and didn't replicate his results. It's clear that it was more a issue with analysis, data analysis, than it was the experimentation. Many of the, ideas that Weber had, find their way into gravitational wave detectors today. Ray Weiss did the first detailed analysis of the noise in interferometers and came up with this idea to use an interferometer. And so it's been a sustained, effort by hundreds and ultimately thousands of scientists to get those levels of sensitivity.
Nice. I have one question, because I think I remember that we still haven't found um, one particular detection of a binary, which is like, is it like neutron star and black hole? Is it that one that we haven't found evidence for it yet?
No, we've got all those now. So we have
Oh, okay.
Yeah. So I didn't really talk about numbers overall because I was skipping over things, but we made 90 detections in the first three observation runs, 90 detections, three in '01, 11, and then 79 or something like that. Depends on how you're counting. And in '03, we made how many? Yeah, no, sorry. Yeah, 79, something like that. And now we made over 200 detections in '04. And this curve, this rate of this curve going up each time, the inflection point, um, is a function of this reach into space. And so first neutron star black hole binaries, we saw two in in '03, and we've seen more in '04. So yeah, so that neutron star black hole binary systems are indeed, yeah, understood. All those pairings are understood. But we've only seen mergers. We haven't seen gravitational waves from neutron star spinning neutron stars, from pulsar gravitars, say. We haven't seen burst type sources. We haven't seen the stochastic background, nor do we really expect to see a stochastic background, certainly from slow roll inflation, say. But maybe the sum of all astrophysical black hole mergers may be a nice source in '05 for us, possibly.
Yeah. What's the astrophysical source you would
Hmm.
most like to see detected? Like, what's the detection that would excite you the most right now if it was made today?
Well, that's any additional source of these potential sources are crucial. The unknown one is probably the most exciting. I mean, that's always what people hope, but you never know when that's going to come. It depends. It's partly a function of rate. It's part of a function of the frequency band you assess and the noise at those frequencies. But of these sources that we expect, I mean, I'd really like to see this continuous wave source. Right now, we analyze for both unknown neutron stars, or arbitrary directions in the sky, arbitrary spin downs, while constrained within some expectations. And if you're looking at a neutron star for a year in some particular direction in the sky, you have to account for the spin down, account for the amplitude modulation, the Doppler shift that comes from the rotation of the Earth. And so it's very compute bound search. But we do look at neutron stars that we know of because we know where they are in the sky and we know what their spin frequency is and we know their spin down. So we can fold those and get really deep limits on them. We've been able to limit a hemispherical mountain on one side of a neutron star relative to the other for something like 100 neutron stars or so to be less than a millimeter on one side. So they're really, really spherical objects. Otherwise, we would have seen them already. So they're cool limits, but I'd love to see that source because I think that will tell us about the equation of state of neutron stars. So Jess has a question.
Thank you. Yeah, I wanted to just thank you so much for this talk, Michael. I really enjoyed the pace and the level of detail. So thank you. It
Thank
was a talk. I have maybe one or two questions coming to you from someone who works a lot with radio interferometers.
you.
There's a sort of naive question I've always wondered about gravitational wave interferometers. I mean, you were talking about strain and ring detectors, and one thing I've always wondered is gravitational waves do not distort time, they only distort space. Is that right?
So gravitational waves distort space and time, coupled space time. Absolutely.
So then my follow-up question is, does that not sort of negate how the gravitational wave interferometer kind of works in a sense like, okay, maybe the distance along one arm has changed, but the time has changed as well. And maybe that, given a constant speed of light, can erase your signal entirely?
Yeah,
Or
so that I mean, we think of it just the way you're thinking of it, right? Which is a displacement in the interferometer that space like the length changes. That's a convenient lab frame way to think about what's happening. To a relativist, they would say, "Well, the length isn't changing at all. It's the metric that's changing." So you could equally say I see the time delay of the light relative from one arm to the other. You could think of it that way and not talk about space at all. So in terms of just a coarse interpretation of what's going on in the interferometer, it's really more just a convenient heuristic in which we describe it. But often you'll calculate, if you just write down, you'll ask, what's the time delay of the light returning at the photodiode? And so you calculate it simply that way. So, a sort of related question that people have, which is I thought you might be going this way, is doesn't the gravitational wave expand the wavelength of the laser that you do to sample? How do you make a length measurement if your ruler is changing too? And yes, it does change the length of the wavelength of the light too, but there's a difference between the storage time of the light and the storage time of the signal in the interferometer, and that helps you. Basically, if the arm length, if you consider the storage time of the light for 280 bounces or so, it gives you some smallish number relative to the storage time of the gravitational wave, given its wavelength and frequencies that it's tracking through. And so you can think of basically new wave fronts go in that are 1 micron in the arms, and they resonate in the arms, and then they get out. And a gravitational wave may move, let's say it's expanding one arm, the X arm, and contracting the Y. And then new wave fronts come in after that storage time for those photons. They're 1 micron, and they go in, and they're getting expanded in the X arm and contracted in the Y. And then finally, that thing turns around after some many cycles of that. And so relative to the storage time of the light, the gravitational wave is modulating at lower frequencies. It becomes more and more important at higher and higher frequencies. If we say sampled our detectors at not just 16 kilohertz, but we went up at, I don't know, 74 kilohertz or something like that, or 256 kilohertz, and we looked at the interferometer at 32 kilohertz, then you can get a source on the zenith in which the effect is absolutely happening at 32 kilohertz. It's happening, it's expanding and contracting the arms at 32 kilohertz. And you have a beautiful length sensor at 32 kilohertz, but the effect on the arms is completely undone by the effect on the light. You have a null on the zenith. You can't see that source at all. So I think that was a related kind of issue that people also ask in the internet.
Mm-hmm. Thank you, Michael. I know we're a couple minutes after the hour, so I might leave it there just to respect your and everyone's time. But thank you again so much.
All right. Thanks everyone for joining. Appreciate it.